Hello. Okay, we just defined in the previous slide the effective action. The definition is given here, which is a Legendre transformation of Zj, and the Legendre pair is phi classical and J. So you see that as a general property of Legendre transformation, J is given by derivative of gamma with respect to phi CL, and phi CL is given by derivative of Zj with respect to J. Okay. Now, as a consequence of this equation, we see that if you set J equal to 0, then if you set J equal to 0, then okay, before that, recall the definition. According to the definition of phi CL, what it actually means in terms of J. This is a transformation that relates phi CL and J. This whole expansion. There are more terms like a higher order in J terms. So this is the 0th level. This is the first order, and then you have second order, third order, and so on. So that's a relation between phi CL and J. Now, if you set J equal to 0, then all this linear order, second order, cubic order, all those terms will vanish. Only this term will remain. Only this will remain. Which this particular expression is for a particular theory, phi cube theory, but the general construction that we are discussing is more general. I mean, it's for any field theory. For the phi cube theory, we have calculated the vacuum expectation value of the field and found that pole, which is a constant because it's a Lorentz invariant theory, and we have chosen a Lorentz invariant vacuum. So at J equal to 0, one gets the phi classical is basically the tadpole, a constant, which is the new value of the field where the potential is extremized or the effective action is extremized. So del gamma del phi CL is 0 when J equal to 0, right? So so the statement is moreover, if you set J equal to 0, then this term is 0, and Zj is also 0 because Z does not have any vacuum diagrams. So this is the expression for Z. So this is also 0. And therefore, gamma phi CL is also 0. So the statement is that when J is equal to 0, then we call let's call it phi CL 0, which is basically the vacuum expectation value of phi hat x at J equal to 0. This extremizes gamma. Gamma itself is 0 at phi CL 0, and del gamma phi CL del phi CL at phi CL 0 is 0. So phi CL 0 is basically a solution of the effective action. It's an extremization of the effective action. If that solution is constant, which corresponds to a Lorentz invariant vacuum, then as an example, we have calculated that in this in our quantum field theory, phi cube theory. The entire calculation, what was inbuilt in that entire calculation was that from the very beginning that the vacuum that we are choosing around which the perturbation expansion was being formulated was Lorentz invariant. But you could actually expand the theory around any classical solution and then calculate Zj and so on, in which case the analog of this contribution at j equal to 0 will not be a constant, but will have a space-time dependent profile. And but those calculations, those results will be will involve quantum corrections like loop diagrams, right? So if you start out with a classical solution in the classical theory, a non-trivial classical solution which breaks Lorentz invariance, and then shift and then expand the action around that, and then set up the perturbation theory and Feynman diagrams and so on, then that classical solution, this expression will have information about that classical solution, and also a quantum corrections on top of that. So that will be the quantum shifted or quantum modified. And then in that case, phi classical x will have a non-trivial profile, will not be a constant, and that will involve the quantum corrected solution for the effective action. Okay. Now, if you take so you can demonstrate that for the Lorentz invariant vacuum, the existence of effective potential. So this effective potential can be, you can show that it exists in gamma, and that is relevant because in the Lorentz invariant vacuum, phi classical 0 will be constant, and therefore only the effective potential will be relevant for this extremization. So what you do is perform a derivative expansion of gamma. What it means is that write gamma phi CL as gamma phi CL as an integral dx. Then you write it as an expansion in powers of derivatives. So the leading term will be derivative to the power 0, which means is a function of phi CL. So that let me call V effective phi CL. Then second order derivative, say A of phi CL del mu phi CL del mu phi CL. Since I'm considering a Lorentz invariant vacuum, so the effective action will be if it has to have a one derivative term, then the one derivative will have a mu index. That mu index has to be contracted with something, and if that is a function of phi CL, then that breaks Lorentz invariance. Therefore, it has to contract with a derivative. So if you are looking at Lorentz invariant expressions, then there is no background field which can contract with derivatives of phi CL. In that case, this will be the expression. So higher order terms will be higher order derivatives in phi CL. And then when you choose the Lorentz invariant vacuum, then phi CL 0 will be constant in vacuum phi CL 0 is a constant, and therefore what we will have is extremization condition will simply be effective del V phi CL at phi CL 0 must be 0. So in this sense, this has a this is an interpretation that it is an effective potential. It is an effective potential, and then once we find either we know what effective potential is. If we know the effective potential, then we extremize it and find phi CL0, and or the path that we had taken of coming from starting from the classical action and then doing all this Feynman perturbation theory. There also that way also one can calculate one in that case one can calculate V effective potential, and phi CL0 is basically this expression given here with J equal to 0, which means the first line. So then in this case we can choose just phi CL0 equal to 0 by shifting the origin of phi CL equal to constant, right? I mean, by giving the proper shift in phi CL, we can shift the origin of phi CL to 0, so that origin of phi CL, so that phi CL0 is equal to 0. So then you can do a Taylor expansion around that configuration, and that Taylor expansion will be a functional Taylor expansion functional Taylor expansion of gamma phi CL around phi CL equal to phi CL0 equal to 0. We will look at that later, but now to make connection with what calculation we did earlier, let us look at, this is the definition of we have given the definition of gamma. Then this is a derivative expansion. You could also expand in a different way in powers of phi CL. So in which case you will have a phi CL to the power 2 term, phi CL to the power 3 term, and so on. Those are, you are counting the powers of phi CL instead of the derivatives of phi CL, powers of derivatives of phi CL. So if you look at the powers of phi CL, then let us look at the quadratic in phi CL term. From the definition of from this result, if you take a J derivative on both sides, then in this side you have del gamma del phi del J, and on this side we have a delta function, and so del Jy del gamma phi CL del phi CL x is minus h bar del x minus y. Right. Now this okay, just the left hand side. Sorry. This left hand side can be written by using the chain rule as in the following way. It is del phi CL z del Jy del 2 gamma phi CL del phi CL z del phi CL x. Right, and then use the Legendre transformation where phi CL is derivative with respect to derivative of z with respect to j. This expression, you can use that in the first factor then it will be I times dz del to zj I del jy I del jz, because I'm writing phi cl as del z del j with some factors of I. Okay, and then this one. So what it means is integral dz del to gamma phi cl del phi cl z del phi cl x times del to z j I del jz I del jy. So here I have a coordinate y and the other was one is z. Here it is z. Sorry, I have x and z. Here z and y. Okay, and the z is integrated over, and on the right hand side I have I h bar delta x minus y. You see, this one we know is the connected two-point function, connected two-point Green's function, and this has this is basically the second order derivative of gamma, which has the information of the quadratic piece in gamma. Okay, in some sense, right? So we have shifted the origin of phi cl in such a way that that j equal to 0 corresponds to phi cl equal to 0, because we have chosen phi cl 0 to be 0, right? So what this would mean that I calculate this at 0 and this at 0, which is basically I'm calculating left hand side at j equal to 0. When I calculate this at j equal to 0, this is the two-point Green's function. And when I calculate this as at j equal to 0, which corresponds to phi cl equal to 0, then that gives you the coefficient of Taylor series expansion of gamma around phi cl equal to 0. That's the second order term. Okay, coefficient of the second order phi cl square in the Taylor expansion. So in that sense, and that in some sense is the inverse of this Green's function, because on the right hand side I have an identity. I have like 1, right? If you view it as a matrix, then delta x minus y is like an identity matrix, diagonal matrix. Okay, x equal to y. So view this as a matrix with a matrix element x and z. This is matrix with matrix element z and y. So it's a multiplication of two matrices, z being summed over, it gives you an identity. So then we have to invert it to get this expression. So that is the exercise that we're going to do now. So let me write it here. This at 0, which is basically extremization, and this is j equal to 0. Okay, so let me write it more explicitly. This is at phi cl equal to 0. And this one is at j equal to 0. When you write j equal to 0, then that quantity is nothing but the connected two-point function. And this connected two-point function has a momentum representation, which is given by h bar times dp over 2 pi to the power d to the power pi dot x minus z minus y times g tilde c2 p square, where this is, we calculated 1 over I times 1 over p square plus m square plus pi of p square minus I epsilon. That is the complete exact propagator in momentum space, where pi is the self energy. So now let us use it. We shall use this, but to write it more systematically, to do the inversion, actually, we take the form of a power series form of gamma phi CL, right? So series form of the effective action can be written as gamma phi CL is equal to half integral dx dy phi CLx gamma 2 x minus y phi CLy, and then order phi CL cube. If you write it this way, so this is, you can recognize that this is a non-local expansion. Okay, it's like a Taylor expansion of gamma around phi equal to 0, and because I'm expanding around the extremum, where the extremum is phi CL equal to 0, there is no linear term, and therefore it starts with the quadratic term. Gamma, so ideally speaking, more generally, gamma phi CL, if you Taylor expand around phi CL equal to 0, then the first term will be phi gamma at phi CL equal to 0, that is 0. But we have shown that okay, then the first term will be phi CL linear in phi CL, and the first derivative of gamma with respect to phi CL, and then these terms. Now, since we have chosen phi CL equal to 0 to be the extremum of the effective potential, it is we are doing a Taylor expansion around that point, then the first term phi gamma at phi CL 0, which has been chosen to be 0, is 0, and then the first order derivative is also 0. So this is the leading term, and then phi cube and so on, right? Now from here you can show easily that if you take two derivatives of gamma, you can do double derivative of gamma phi CL with respect to phi CL x, phi CL delta phi CL x delta phi CL y, and then it is if you take this double derivative, you will get a gamma 2 x minus y, and then that same thing can be written in momentum space. Just do Fourier transformation, will be e to the power I p dot x minus y gamma tilde 2 p square. Yeah, it's a Lorentz invariant quantity. It must be this way. Now, and you substitute this form in this. So you basically, what I'm asking is that you substitute. So take this equation, then substitute for this factor, this expansion. I mean this momentum space expression, and for this one you write this momentum space expression, and then your equation will be in terms of g tilde gamma tilde 2 and g tilde 2 connected. Okay, so that is what we we are supposed to do. So let's write integral dz, then this double derivative, integral dz, and then this double derivative is integral dp by 2 pi to the power d to the I p dot x minus z gamma tilde 2 p square. And then the second, then the g2, then this factor, which is given by this. So replace p by q, h bar integral d q by 2 pi to the power d e to the power I q dot z minus x, right? This is zx, yes, this is z y. So this is zx and this is zy. This is zx and this is zy. So let me write this to be zy. Okay, and g tilde to c q square. That is equal to I h bar delta x minus y. Then you perform, let's look at the z dependence. Z only appears in this phase and nowhere else in these two phases. So you can perform z integral. It will give you a delta function. Here it is minus p, here it is plus q. So it will be delta p minus q with a factor of 2 pi to the power d. Then you will be left with the one of these two will get cancelled, and you will be left with 1. So 1 factor of 2 pi to the power d downstairs, delta p minus q. Okay, before that I have to write p integral. P integral I have written. Then e to the power I p dot x minus I q dot y, then gamma tilde to p square g tilde to c q square is equal to I h bar delta x minus y. Okay. And then you integrate, perform the integral of q, which gives you integral dp over 2 pi to the power d to the power I p dot x minus y gamma tilde to p square g tilde to c p square is equal to I h bar delta x minus y. Right? So since the right hand side is a delta function, left hand side should also be a delta function, and this is sufficient to do the to get the delta function. So this must be 1, right? That this is delta function. So this must be 1. And therefore gamma tilde 2 p square is I, there's a factor of I here. What happened to h bar? That let's see. Right, so this h bar must have cancelled. So this h bar and this h bar has cancelled. So I should have only a factor of I here. So this is I times g tilde 2c inverse square, which is given by minus p square plus m square plus pi of p square minus I epsilon. So you got the result for gamma tilde 2. You substitute it back in the expression of gamma, right? This is gamma 2 x minus y. Gamma 2 x minus y has this expression, and we have got this expression right now. So substitute all of this in this expression for gamma. That is half integral dx dy phi cl x, and then we have this gamma 2 x minus y, which is given by this. So integral dt by 2 pi to the power d to the I p dot x minus y times gamma tilde to p square, which is given by minus p square minus m square minus pi of p square plus I epsilon. And then we have phi cl y. This you can write as half dx dy dp by 2 pi to the power d, then phi cl x, and what I'm going to do is to write this phase factor on is to write this phase factor on the right hand side of this factor, and then write p square. For each p square I write differential operator with respect to y. Okay, so that is how I'm going to manipulate it. Then I must be writing so if I write this phase factor on the right side of this thing, then p square is nothing but double derivative with respect to y, but then that will bring down an double derivative with respect to y will bring down 2 power of minus I square, which is minus, so that is minus p square. So minus p square is equal to del y square minus m square minus pi. P square means minus del y square. So we are in the space-time interpretation now. So let's not do I epsilon anymore, right? I epsilon anymore. So then e to the power I p dot x minus y times the factor of phi cly. Okay, now there is no other no p dependence anywhere other than this phase, and therefore p integral can be done, and that will give you a delta function delta x minus y. So that is half integral dx dy phi cl x del y square minus m square minus pi minus del y square acting on delta x minus y phi cly. Now, to calculate this expression, the best way to do this, I think, is This operator depends only on y, and therefore it does not act on phi x. So integral phi x can go through this operator. If you do that, then I will have 1/2 dy, then del y square minus m square minus pi of minus del y square. This object acting on integral dx phi clx delta x minus y times phi cly. This operator was not acting on phi cly, it's acting only on delta x minus y. But then this is nothing but phi cly. So basically you get a quadratic piece phi cly times phi cly times this operator acting on phi cly. So I'm writing it this way. Half integral dx. I'm just writing instead of y, I'm writing x. It's a dummy variable minus m square minus pi minus del squared phi clx. Then you can do an integration. This is del mu del mu. If you do an integration by parts, then basically you can distribute this derivative into two. So this is double derivative on phi, but if you do integration by parts, it will be del mu phi, but with a minus sign. Right. So this is same as minus half integral dx del mu phi cl del mu phi cl plus m square plus pi of minus del squared times phi cl square. This will be the term, and I'm calculating only the quadratic piece, so I should not be writing an equality here. It's a I'm calculating only that. So there will be a cubic order terms, right? Phi cube and phi cl cube and so on.